Hello, I'm Ralph Gable of the Electronics for the Inquisitive Experimenter YouTube channel. This is the fourth in this series on design end-to-end. In the last video, I started the process of the initial design with the input and output amplifiers function blocks. If you missed that video, I've put a link to that video up in the corner for you. In this video, we're going to cover the initial design of the indicators function block. I was going to cover both the indicators and the power supply function blocks in this video, but that got way too long, so I decided to break it into two videos. Now, like any design process of any device, there are the loopbacks, the discoveries that cause a change in direction or the intended implementation. Now, these might be minor changes, or they might be major changes which stand the entire design on its ear. Well, this one is no different. In this video, you will see some major changes in the implementation of this design which ripple through the entire thing. If you have questions or comments, please feel free to add a comment to this video. If you find this video helpful, please click on the like and don't forget to subscribe. Now, as we continue our design, let's dive into the indicators function block. Well, it turns out that there is a whole lot more to the whole level meter thing than I thought there would be. In the second video of this series, I had decided to use a microcontroller to manage the indicators. I chose an Arduino Nano Every microcontroller project board for the task, well, just for the simplicity of development. In the intervening days, the software guy spent some time, well, a lot of time, working on the actual software to do the task. I mean, why design in a device that can't do the task assigned to it? This is where he discovered the complexities of the whole thing. The biggest issue was the output level meter. We thought that this should be in real dBu, which spoke to us of an RMS calculation of the audio. But the audio he had to work with had a DC component to it, which turned out to be a critical portion to deal with. In order to get an accurate RMS value, he absolutely had to know the exact DC level that the audio was riding on. So I thought to myself, okay, we'll use an RMS to DC converter in front of the Arduino. Well, that turned out to be a very expensive item. The cheapest chip I could find was over $10, and some of them were as much as $250 and more. Okay, total system reset. Now was the time to investigate how other people do things in the professional audio mixers. So I went out on the internet and I looked for schematics of existing analog mixers. And to my surprise, they don't actually indicate RMS value. They indicate an average value as determined by a very simple circuit. The same circuit that I found in the schematic for an analog mixer is also in the datasheet for the LM3916.bar display driver chip. Now, there's a lot of great application information in that datasheet. For that reason, I put a link down in the description so that you can benefit by it too. Now, by the time I put all of this analog pre-processing in front of the analog inputs of the Arduino would be serving as nothing more than just a set of comparators to drive LEDs. An awful lot of horsepower to be doing nothing more than acting like a comparator. And the cost of the Arduino Nano Every, well, they're about $15 or so, depending on where you get it. And comparators are 50 cents a piece, and I only need 2 of these. So all of this has stood my concept of the implementation of the indicators function block right on its ear, and the effects ripple back through the whole rest of the design. The first and most important effect is that the whole design is moving from a single supply to a differential supply. Well, what does that mean? It means that I need both a positive and a negative power supply voltage. The negative supply of the op amps will be connected to a negative voltage supply instead of ground. But that also means that all of the connections to the pseudo ground now get to be connected to the real ground. The LM39, 14, 15, and 16 dot bar display driver chips would be a great option to use for driving the LEDs. It has all of the comparators and all of this associated circuitry all in one chip. Unfortunately, as handy as they may be, they're obsolete. So, we are stuck with using comparators, just like they did in one of the analog mixers I looked at. Now, there are two aspects to the indicator's function block. There are the peak indicators, and there's the output level meter. So let's start with the peak indicators. This is where the beauty of datasheets shines through. Going to page 12 of the LM3916 datasheet, we find a half-wave peak detector in figure 18. It looks like this. This provides a DC output which tracks the peak value of the incoming signal. Now, I've simulated this using LT Spice. There's a 50 cycle burst of 1 kilohertz 2 volt peak signal on the input. This stops at 50 milliseconds. The output reaches 2.2 volts in about 3 milliseconds. Notice also how the output trails off slowly. We have 2 volt peak on the input and 2.2 volt DC on the output. We will have to accommodate this 0.2 volt difference in the stuff that follows. But now that we have a means to capture the peak voltage of the audio, we need to turn on that peak LED at the right level. To do this, we will use a comparator. But what level is that? The peak indicator is supposed to illuminate at plus 6 dBu. So we have to ask the question, what peak voltage represents plus 6 dBu? Well, let's calculate that. First, the RMS value is 0.7746 times 10 brought to the 6 over 20 power, which gives us 1.55 volts RMS. Now we translate this RMS value to peak voltage by multiplying it by the square root of 2, which gives us 2.185 volts peak. But this peak detector gives us 2.2 volts out with a 2 volt peak signal in. So our compare voltage needs to be 0.2 volts higher than the actual desired threshold voltage. This gives us 2.385 volts. We will use a voltage divider to provide this reference voltage to the comparator. Now, I'm going to choose to have 1 milliamp flowing through the divider. Okay, so you ask, why 1 milliamp? Well, first, we want enough current to be going through the voltage divider so that it isn't disturbed by minor stuff going on around it. We don't want the output of the voltage divider to be influenced by the load impedance of what it's feeding either. The input impedance of its client is in parallel with the output resistance of the voltage divider. Second, we don't want to use too much current so as to generate more heat or add additional load to the power supply. So my personal feel-good number is 1 milliamp for this design. Now, I've used less in the past, but rarely more. So if we want 2.385 volts out of our voltage divider, and it has 1 milliamp running through it, this means that the output resistor must be 2.385 volts divided by 1 milliamp, or 2.385 kiloohms. Now, we peruse the list of standard 1% resistor values to find what is the closest available value, And we find that there are two of them that are pretty close, 2.37K and 2.4K. Well, go figure, 2.385K ohms is dead center between the two possible choices. So I choose 2.4K ohms. And you say, okay, why did I choose 2.4K ohms over 2.37K ohms? I don't know, because it feels good to me. The voltage will be a mere 0.6% away from our ideal regardless of which one I choose. And besides this, there's nothing precision about the operation of a peak indicator LED. The input resistor depends on the power supply voltage, and we haven't determined what that will be yet. We will have to choose the input resistor value for this voltage divider once we get the power supply portion of this design and know our supply voltage. So the overall design, including the comparator, looks like this, as shown in the LT-SPICE simulation. Now, for the sake of this simulation, I assumed a 9-volt power supply rail. The size of C1 determines how quickly the peak indicator will respond to inputs, as well as the length of time the LED stays illuminated. The larger the value, the slower the response, and the longer the LED will stay on. R4 also determines the length of time the LED will stay illuminated. The larger the value, the longer the LED will stay on. Now, I increased the value of this from the original 1 megohm to 30 megohms to extend the time the LED will remain illuminated when the peak value exceeds the set limit. Now, this value may change again depending upon the performance of, well, the real circuitry. Here is a simulation output for this circuit using a 50-cycle burst of 1 kilohertz, which is just slightly above the threshold voltage level. You can see the burst here. And here, this is the output voltage of the peak detector. And this is the current through the LED here. You can see that the LED will stay illuminated for a period of time after the peak voltage goes away. This completes the initial design of the peak indicator's portion of the indicator's function block. Now we get to turn our attention to the output level meter. As I said in the introduction, the output level meters actually indicate the average signal level, not the RMS voltage. One of the levels that we have to be concerned about is minus 30 dBu. And this is a relatively small voltage. It amounts to about 25 millivolts. So it would be real nice to have some gain associated with whatever we use to give us the average voltage. If we go back to the LM3916 datasheet, we find a really nice little design, but it has too much gain. Now, I could play with the values to get what I'm looking for, but I chose to see how other people did this same thing. I went out to the internet and I rummaged around looking at the schematics of various analog mixers of various vintages, and eventually I found this circuit, which gives me exactly what I am looking for according to the LT-SPICE simulation. So I'm going to borrow this design for my own project. Why reinvent the wheel? The last step of this part of the design is to determine the output voltage from this averaging amplifier for each of the target levels meter LEDs. We will need these voltages for the next step. Now, I've done this, and here are the simulation results. At minus 30 dBu, we have 125.8 millivolts. At minus 20 dBu, we have 405.6 millivolts. At minus 10 dBu, we have 1.29 volts. At minus 3 dBu, we have 2.9 volts. At plus 3 dBu, we have 5.79 volts. Now, designing the comparator circuit that drives the LEDs is the next step in designing the level meters. So we have an averaging amplifier that puts out a DC level commensurate with the average voltage level of the output signal of the mixer. Now we have to take this DC voltage and turn it into illuminated LEDs at their specific levels. Now we could do this with a fancy schmancy current source circuit and so on to drive the LEDs, and that way the LEDs are always at the same brilliance. But I'm going to just keep this really simple. Each LED will be driven by its own comparator. This means that we have 5 comparators for our 5 LEDs. Each comparator will share the output of the averaging amplifier. Each comparator will get its own reference voltage commensurate with the level that they represent. And this is where the voltage levels we just noted a few moments ago come into play. I'm going to provide these reference voltages through a multi-tapped voltage divider string. We will design this string next. The first step in its development is to decide on the current that we're going to be putting through the voltage divider. I will choose 1 milliamp, just like I did with the peak indicator's voltage divider. We start at the bottom and work our way to the top. The first voltage level that we're interested in is 0.1258 volts. This is produced across a resistor with 1 milliamp flowing through it. So the resistor value would be 0.1258 volts divided by the 1 milliamp, or 125.8 ohms. Well, that's not exactly a standard resistor value. So we go out and we look for the standard 1% resistor value that might get close to this. The closest one is 127 ohms. At 127 ohms and 1 milliamp, the actual voltage that will be present at tap 1 will sit at 0.127 volts, which is within 1% of our target value. Now we move to the second tap, and the voltage on that tap wants to be 0.4056 volts. So we calculate the voltage difference between the actual voltage at tap 1, which was our 0.127 volts, and this one, which wants to be at 0.4056 volts, and we get 0.2786 volts. Now this is dropped across a resistor that has 1 milliamp flowing through it. So we have 0.2786 volts divided by the 1 milliamp, or 278.6 ohms. Again, not exactly a standard resistor value. So we go out and we look to find the closest standard 1% resistor value is 280 ohms. The voltage drop across this resistor will be 0.280 volts. So the actual voltage at tap 2 is the actual voltage at tap 1 plus this 0.280 volts drop across this resistor, which gives us 0.407 volts, which is within 0.35% of our target value. Now, I'm not going to go through all the rest of the taps. We just continue this same process tap by tap for the next 3 taps. The final the voltage divider looks like this. All of the nominal output voltages are within 1% of their target values. Now remember, this is not a precision measurement device, so we're totally good to go on this one. The total resistance of all of the resistors in this string is 5,784 ohms. We're going to need to know that later. The last resistor to be specified is the one that goes between the top of this string and the power supply. Now, I'm thinking that I might use a trimmer pot for this so that I can do some adjustment. The last thing to be determined is the actual identity of the comparator that we'll be using. I need a total of 8 comparators. I will choose to look for chips that have 4 comparators in a package, so I will only need 2 of them. Because I'm going to be using these to drive LEDs, I think I will choose the more common open collector or open drain output, which has enough sync current capability to handle the LED current directly. I'm figuring on, well, about 10 milliamps or less to drive each of our LEDs. By putting the reference voltage on the positive input of the comparator and the input voltage on the negative input, the output of the comparator will go low when the input voltage exceeds the reference voltage. With the LED and its current limiting resistor residing between the plus 12 volt input voltage and the output pin of the comparator, the LED will illuminate when the comparator's output is pulled low. Then lastly, we want to be sure that the comparator can handle the power supply voltages that I will be using. I ended up with an LM2901DR from Texas Instruments. This can handle up to 38 volts, so the LEDs connected to the plus 12 volt input won't bother it when the output goes to its high impedance state. The overall level meter circuit looks something like this. You can see the resistor string that provides the reference voltages. The comparators are here driving the LEDs. When the input voltage is below the reference voltage, the output of the comparator is going to be in its high impedance state and the LED will be off. When the input voltage rises above the reference voltage, the negative input of the comparator is now above the positive input and the output of the comparator is pulled low and the LED turns on. We have completed the initial design of the indicator's function block. Now, this took a little bit longer than I thought it would. In the next video, I will complete the entire design with the power function block. I will talk about how to get a negative power supply voltage when all you have is a positive input voltage. I will also answer the question, how do I get that VCC over 2 voltage you spoke of in the last video? Well, okay, true, we no longer need it for this design, but I do make good on my promises. If you found this video helpful, please click on the like and don't forget to subscribe. Thank you so much for watching. Until next time, Toodle-Oots.